All right, this section of the review, I want to tie together some loose ends. I want to go over some basic, important conceptual things, as well as review some things that didn't explicitly come out in other parts of the review. You may recognize these slides as being those that David presented in class when he gave a guest lecture a week ago. I want to go over these same slides and point out anything that he may have overlooked when he did his guest lecture. So, one of the applications of Laplace transforms, in addition to being able to apply them to circuits, which comes in the next section, we can apply them to systems, linear systems. And this is not unique just to electrical engineering. Let me find my words. But it's also useful in mechanical engineering and any system of equations that represent a linear system. So systems that represent equations that represent a linear system are typically linear differential equations, and so we can take their transform, put them in the Laplace domain so that we have an algebraic equation. And basically, when we get a solution, it should be of the form where we have a polynomial in the numerator divided by a polynomial in the denominator, known as a rational function, when the numerator polynomial is of lower order than the denominator polynomial. So this is our function as represented in the S domain with a rational fraction. So a typical Laplace function, here it is shown in polynomial form. So this is just a typical function in the Laplace domain. The first thing that would be done is we would factor out an a sub n from the numerator and a b sub m from the denominator, represent that as a constant, and then we would factor our numerator in this fashion, and we'd factor our denominator in this fashion. The roots of the numerator are referred to as zeros, and the roots of the denominator are referred to as poles. So the poles of the function would be minus p1, minus p2, and so on. The zeros of the function would be minus z1, minus z2, and so on. And if this is a function that you're going to use to take an inverse transform, then the order of the numerator will have to be lower than the order of the denominator in order for you to do that using a partial fraction expansion technique. But right now, I just wanted to show you what is meant by a rational function, what are meant by zeros, what are meant by poles. Now, the reason to look at a function this way is that the poles in the S domain tell us something about the behavior of the function in the time domain. So here's an example with some numbers. So you see the numerator, denominator. First of all, the constant is factored out, written as 8 over 2 and later as 4. And then each term now has its highest order term in S equal with a coefficient of 1. So the numerator is factored into 5 and 10. The denominator is factored into 1, 2, 3, and 4. Now if you're going to do identification of poles and zeros, you need to factor both numerator and denominator. So the question is, what are the poles and zeros here? In this function, we have zeros at minus 5 and minus 10 because those values will make the function go to 0. We have poles at minus 1, minus 2, minus 3, and minus 4, and those values will make the function go to 0 in the denominator and the overall function go to infinity. So note that they are all negative, and in this particular example, they are all real. So the options with poles and zeros, you can have first order real negative roots. You can have higher order roots, so that might be like an s plus 1 quantity squared. That would be a second order negative real root. You can have complex conjugate pairs, and you can have roots at 0 or roots at the origin. So that would be like if we had just an s in the denominator, that would be a pole at 0. If we had an s in the numerator, that would be a 0 at 0. And the presence of poles and zeros at 0 definitely impact the time domain response, as well as all of these different kinds of terms will have a different kind of response in the time domain as we discussed in the previous lecture. So This is just kind of a restatement of what I already said. As long as the numerator is of lower order than the denominator roots are going to be what determines the time behavior of the system. So will it be exponential decay? Will it be oscillation? Will it be decaying oscillation? So it is possible for poles and zeros to be complex, and the next two slides will illustrate a couple of time domain functions. Or maybe not. Let's see. Oh, okay. So here's a table in your book that shows, for example, a couple of functions in the Laplace domain and what their transform looks like in the time domain. So you can see when we have these distinct real roots that we're going to get an exponentially decaying function, and the decay rate that multiplies time is going to be this a. The time constant would be 1 over a. If they're repeated for each level of repetition, so in other words, for a second order, we're going to get a first order term in t. If this were cubed, we would get a t squared. And then you also get the lower order terms. So this table is showing what would happen if you've already done the partial fraction expansion. So we're assuming we would have a term that would be some constant over s plus a squared. But in general, if you have a polynomial function and you have like an s plus 2 squared times s plus 1 times s in the denominator, you would need to do a partial fraction expansion on that. And that might give you both a number 1 type and a number 2 type. So you might get both of these terms. And in general, you would get both of these terms. While one could always have a constant equal to 0, the most general form, if you have an s plus a squared, if you have a second order negative real root in your denominator of your polynomial, you could pick up both of these terms. Finally, if the roots are complex conjugate pairs, the partial fraction expansion, if you don't complete the square and you do it as complex conjugate roots, it's going to look like this. Now, in class, we used the method where we completed the square of the denominator and we expanded that into a sinusoidal and a cosinusoidal term, both multiplied by exponential decay. In this example, that was not done, and in fact it was expanded as single order complex conjugate pair roots. The numerators in that case will also be complex conjugates of each other. And so you actually only have to find one of these, and the other one will just be the complex conjugate. So when that happens, you basically then end up with this expression, which is a phase-shifted cosine function. Now, you may remember from Circuits 1 that a phase-shifted cosine can be written as a sine and a cosine through the double angle formula. So this is equivalent to completing the square. If you use MATLAB to do your transforms, this is what you'll get. Okay, so here's some examples of the complex plane. The vertical axis is j omega. The horizontal axis is sigma. And so if we have a complex conjugate root of -6 plus or minus j8, that plots as two poles here on the complex plane. If we have a negative real root of 10, that plots right here as -10. If we have a 0, that plots with a little open circle. So poles are x's, zeros are circles. Well, another important use of functions in the Laplace domain, when we have rational functions, is that it allows us to determine the initial and final value of the function in the time domain. And so that's where the initial and final value theorem come in. Basically, it allows us to use the function in the Laplace domain with the theorem instead of transforming backward to the time domain. So here is the initial value theorem. It basically says that if we want the initial value of a function t, in other words, the value of that function at 0 plus, that we take the limit of s times f of s as s goes to infinity. So a simple comment about allowing s to go to infinity. As a general rule, it is easier to let things go to infinity if they occur in the denominator of the fraction. So you probably want to find the highest order term in S in your polynomial and divide both numerator and denominator by that. So if it's s to the fourth, you'd want to divide numerator and denominator by s to the fourth, each term by term. When you do that, you basically create a situation where most of the terms will either go to zero or you'll get a constant. And so that enables you then for it to be much easier to allow s to go to infinity. The same on the final value theorem. Here in the final value theorem, you're finding out what is the final value of this function of time as time goes to infinity. In that case, we'll take the limit as s goes to 0 of s f of s, and that would give us the final value of the function. Here are some examples. Here's an example of a function f of s. We multiply that by s to get the following result, and then we take the limit as that goes to 0. So as s goes to 0 here, this term is 0 and this term is 0, making the overall function 0, meaning the function at infinity or the final value of this function is 0. If you want to do the initial value theorem, you would take the limit as s goes to infinity, and here's what I'm talking about, that it's kind of hard to evaluate infinity over infinity. So if you multiply out the denominator into all three terms and get the polynomial for the denominator, and then you divide numerator and denominator by s squared, you'll find that it's really easy to see that that function approaches 6. Here are some more examples. In this example, we just have a second order polynomial in the denominator. We take s f of s. It's now easy to see that if we let s go to 0, the numerator goes to 0, so the whole function goes to 0. So the final value is 0. If we let s go to infinity, in this case, because the order of the denominator is clearly lower than the order of the numerator, that function will approach 0 at 0. This is another example where we have what's different here is that you notice in this function we have a 0, or we have a pole at the origin. So we have a pole at 0. We now multiply that by s. We get the following expression. And then we apply the final value theorem. We find that we get a constant for the final value. Okay, so this is kind of interesting because 1 over s terms represent in the time domain integration. And so this would be like a circuit that contains an integrator. And so whenever we have circuits that contain integrators, we know what they tend to do is they tend to introduce DC offsets. So you will notice that your function evaluated at infinity is equal to 60. The other thing that this can be viewed as physically is a 1 over s term represents a step function. So somewhere in this system a step function was introduced that produced a DC offset, which shows up when you evaluate this at infinity, this 60. Once again, now if you take the limit as s goes to infinity, because the denominator is of higher order than the numerator, that function will go to 0. And I believe that's the last example. Yes, that's the last example of initial and final value theorem. It's pretty straightforward as a general rule. It's just a matter of memorizing the definition and being able to apply it to a function, which is usually fairly simple and straightforward. But I do want to know that you know the definition of initial and final value.